Lesson 3 of the Thermodynamics Year 13 course. This one we are going to be looking at the covalent character of ionic compounds. So far, going through GCSE in Year 12, you've learnt about ionic compounds, covalent compounds, and obviously they're very different. Ionic compounds are donating electrons one to the other and accepting electrons. Covalent compounds are shared and never the twain shall meet. But actually, it's not that easy. And actually, what you'll find out is that there's lots of things that are kind of slightly in between. So ionic compounds have covalent character. And as you probably, you remember that covalent compounds can start to be polarized. Okay, so you can kind of sort of think of that as becoming to be a little bit like a spectrum. So if you have a spectrum of ionic and covalent over here, so you're going to start to move towards that. So this is the polarized polar covalent bond. Okay, and this is an ionic with covalent character. So this is what this lesson is going to be about. It's pretty short and sweet. The exam questions tend to be fairly formulaic. Right, before we talk about covalent character, we need to talk about lattice formation enthalpies a little bit more. We need to work out whether they're going to be big or small. Right, so when we did our Born-Haber cycles, we noticed that the lattice formation enthalpy for Al2O3 was extremely high compared to let's say NaCl, which we also did. Okay, so we're going to be able to explain why this is so much higher when we've gone through this slide. So basically, the understanding should be firm from year 11 is that ionic lattice is that lovely little lattice of oppositely charged ions, okay, which are attracted to each other. Okay, so if I just draw that, there's my ionic lattice. There we go. Okay, that's right. If I get it wrong. Okay, so there's my ionic lattice, one little bit of it. And your ions, there's a force of attraction holding each of these ions in place. So this ion is a force of attraction to 6 ions of the opposite charge. So, and the stronger the attraction between these ions, the stronger the ionic bond, and so the higher the lattice formation enthalpy. So more energy will be released when those oppositely charged ions come together to make the ionic substance. So there's 2 things that affect how much things attract. Now, so number 1, high charge. Okay, so if you've got a highly charged ion, it's going to have more attraction for other ions than a singly charged ion. So that's the whole idea about oxygen in this. Okay, so the oxygen is an O2 minus ion. Okay, which means that it has a relatively high charge. It's also quite small as well. So small size is the other piece of it. So if you imagine, so I guess one way to think about this is that oxygen has a very high charge density. Okay, it is a lot of charge localized on a very small sphere. Okay, so it's got high charge density, so it feels a high attraction for other ions. Whereas something like iodine here, if I show you iodine, large wibbly wobbly iodine, it's only got one negative charge spread over the entire of that sphere. So it's like having if you want to think about little magnets, it's kind of one that's going to be weakly attracting all of the other little bits and all the other ions. So here we go. Here's a sort of test example question. So it will be written in a slightly less easy to read format than this in the exam. So why is the lattice enthalpy higher for sodium chloride than for sodium bromide? Right, so the chloride ion is much smaller than the bromide ion. Hence it has a high charge density, hence it is strongly attached to the sodium ion. Right, this is very often a 3-mark question and you must make these 3 points. So number 1 is about the size difference. Number 2, the high charge density, hence more strongly attracted. So make sure you get that logical flow right in exams. However, this all assumes that we have a perfect ionic model. Okay, so you'll see the term perfect ionic model in plenty of the exams as well. Perfect ionic model states that ions are point charges, that is 100% ionic bonding. The ions are spherical, which, as you see if you do electron X-ray crystallography, you'll see that they're not. And there's no distortion electron charge cloud. Okay, so what that means is you've got tiny, like nice little round ions like you saw on the last picture that I drew, little lattice there. Whereas actually you'll quite often see that ions tend to be a little bit distorted. Okay, so you'll find they sort of get smeared out and become more kind of oblate. So why is this important? Well, basically you can calculate your theoretical value for lattice enthalpy. Right, this is what we've done with all of our lovely Born-Haber cycles, and then you can actually measure it. Now, I can't tell you how they measure it. I'd need to go and look that up. But you can measure it experimentally, and what you see is that there's a difference between the two values. So for sodium chloride, the theoretical value is relatively close. That's a pretty good margin of error. Sodium bromide, not too bad. Silver bromide, there is a big difference there. That is 70 kilojoules per mole, so nearly 10% out. So there is something weird going on here, okay? And the theoretical value is less than the experimental value. So there's actually kind of more energy released when those ions come together than you would expect. So what's going on is that there is some covalent character. So purely ionic, okay, so this is our point charges. This top one up here is like our classical kind of cage style ionic compound that we've been thinking about since year 11 with the point spheres, and that's kind of your theoretical model that you calculate. But actually the ions have some covalent character. So what happens is there's actually some overlapping of those ions charge cloud, a little bit like this, and that's where you have an ionic bond which is starting to become slightly covalent. So here's the key idea. So if the anion is large, then its outer electrons are far from the attraction nucleus. So you've got, let's think about this in terms of chlorine, which is your small point charge, and you've got your iodine, okay, like this. Now, so your chlorine has a much tighter grip on its electron cloud because that electron cloud is much more tightly held by the nucleus. Whereas the iodine, its electron cloud, it's much further away from the nucleus, okay, so it's a much bigger ion. And so it means that a positive ion can drag this electron cloud slightly away from the iodine towards itself. So that's what you see in this picture up at the top here. Now, obviously, to do that, it helps if you've got a small cation that is highly charged as well, okay? So if you've got something like lithium, let's say, which is a very small cation, it can get up nice and close to the anion and it can attract away the electron density more. Okay, so smaller cations lead to more sharing and more covalent character. And again, as you'd expect, something with a high charge density, so will also have a lot of attraction. So again, let's say something like, here's a classic example, so aluminium. Again, aluminium 3+. Aluminium is in row 2, and it is highly charged, so if you put it up next to something like, let's say, an iodide ion, it can really pull a lot of that electron density away from that and start to have a much more smeared out charge cloud between the two ions. So there's a summary. I'm not going to read it through to you. You can read that through to yourself, but basically there's sort of various exam questions suggesting why these two values different, and it's because of covalent character. Sometimes you'll see an exam question where it does the first idea where it's saying why is the lattice enthalpy higher for a group 1 chloride than a group 1 iodide, and then it will follow up with, let's say, silver chloride versus sodium chloride. So that's kind of a classic question, and you need to make sure that you don't get your reasoning mixed up between the two.